In the x direction, we just have a component of the tension to the left and force wall x component to the right. So we can get the x component of the force from the wall pretty easily. I'm going to store that value as t. And I can take that times cosine 48. The x component of force from the wall is 9.88 something. I'll store that as x. In the y direction, we have t sine 48. And then we got a bunch of mg's. So 9.8 times 1.3, we've got 2.04 and 4.21. And then we also have force from the wall, y component. And if I plug in the value for tension, we can calculate that straightforwardly. And we get the y component of force from the wall is 63 point something. Store as y, so then square root x squared plus y squared. The force from the wall, 63.79 newtons at inverse tangent y over x, 81.1 degrees above the horizontal. Oh, darn, except I was dumb. There are two chains, so that should be a 2 and that should be a 2. So those numbers are wrong. Dang it. This one will just double. So that's my x component. But this one doesn't change straightforwardly and nicely, so I have to recalculate it. 2t sine 48 minus 9.8 is 1.3 plus 2.04 plus 4.21. Okay, so this is 52 point something. That's why. So my magnitude is 55.67 inverse tangent at 69.2 degrees. Sorry about that. All right. There's another problem. A wooden beam with mass 1.1 kilograms is suspended from two cables. The beam is 1.8 meters long. Cables are anchored at either end. One cable is angled at 67 degrees above the horizontal. The mass is hanging from the beam. Find the tension in both cables, and the angle the second cable makes to the horizontal. So you got wooden beam, mass 1.1 kilograms. There are cables at either end. One is at 67 degrees above the horizontal. You don't know if it's going this way or this way, but it doesn't change the answer. It changes whether the angle of the horizontal is this way or this way, but whatever. So over here, I'll call this T1. We've got mg, and this would be T2. So T2 x component, T2 y component. Yeah. So for torque, I'll get rid of this so we can solve for T1. Set my axis at this left end here. I've got T1 times L times sine 67 degrees minus mg times L over 2 equals 0. The length is going to cancel out. Well, that's interesting. Yeah, so we have T1 sine 67 minus 1.1 times 9.8 times 1/2 equals 0, and we can solve 1.1 times 4.9 divided by sine 67. I get that my first tension is about 5.86 newtons. I'll store that as T, and then we can do force. In the x direction, we have T1 cosine 67 degrees minus T2 x component. So we can solve that the x component of T2 is 2.28 something, store x. In the y direction, we have T2y plus T1 sine 67 minus mg 1.1 9.8 equals 0, so we can get t2y. So that's t sine 67 minus 1.1 times 9.8, move to either side, it's -1, so 5.39, store y, so square root x squared plus y squared gives us a magnitude of 5.86-ish newtons at inverse tangent y over x. Oh, that's interesting. Wait, shoot, what did I just do? Well, I guess it works out to be the same angle. That's interesting. 67 degrees above the horizontal. All right. I wanted to give you this one. It's a modified Atwood's machine. We got a mass 5m on a frictionless ramp. It's angled at 30 degrees above the horizontal. So sometimes modified Atwood's machines can have masses resting on ramps. And it's connected by a string. Hanging mass 2m, 5m. Just a reminder that torque doesn't always equal 0. Good practice. Multi-mass systems come out on the AP exam pretty often. So if you want to find the acceleration of the system, well, let's see what's going on. We've got gravitational force, tension 1, call this tension 2, tension 2, tension 1, gravitational force, normal force, and the ramp is frictionless. So string runs over a pulley, I should specify string does not slip on the pulley. That's important. Yeah, so for if we call the pulley a disk, that's 1/2 mr squared for its moment of inertia. So for torque on the disk, you've got T1 times r in one direction minus T2 times r in the other direction, and that's equal to I alpha, and alpha is A over r, and that's for the disk. For the mass on the ramp, the normal doesn't matter because it cancels out a component of gravity. We have the component of gravity going down the ramp. We have T2 up the ramp. Now let's check our signs. T1 was pulling this way, which corresponds to this mass moving down and this mass moving up. So in this equation, T2 should be positive and the component of gravity should be negative. It's 5ma, and then the 2m. We have gravity going down, which should be positive, and T1 going up. That equals 2ma. Those are all of our equations. R's cancel out. The squared can kill that one. This R can kill those R's. And if we add all our equations together, tensions go away. And we have 2mg minus, oh, that's interesting, 5mg sine 30. Sine 30 is 1/2. So it's minus 5 over 2 mg equals 1/2 ma plus 5ma plus 2ma. So and what do we determine? Well, actually, 5m is going to slide down and 2m is going to go up because this is negative. 2 is 4 over 2, so this is minus 1/2. Oh, and mass goes bye-bye. G equals 7.5 or 15 halves a. So our acceleration is going to be 1 over 15 g. 2m accelerates up, 5m down the ramp. A problem would probably ask for the magnitude rather than asking it awkwardly give a direction. Tension in the vertical section of the string, we can take our equation, 2mg minus T1 equals 2m times A. Just 1 over 15g, T goes bye-bye, m goes bye-bye. We have 2 over T1, it's going to be 2 minus 2 over 15, so 28 over 15. What am I doing? I can't cancel the m's. I need to keep them there because there's no m in this term. That's silly. So we get 28 over 15 mg. And then for the other one, we have this equation. So we have minus 5 over 2 mg plus T2 equals 5m times A, which is 1 over 15g. And then we can calculate, so that's 5 over 15, which is 1 over 3 plus 5 over 2. That would be 2 over 6, and that would be 15 over 6. Yeah, 2 over 6 plus 15 over 6 would be 17 over 6. Hoorah! And then there's one more problem here. So you know the boom of a crane is a uniform 3 meters long. This is the boom. Yep, and this is the tie rope. You notice these angles are complementary. So force of the hinge, we got force of the hinge X, force of the hinge Y. We've got gravitational force on the boom. We've got gravitational force of the stump and other stuff. And we've got tension here. So if we set our pivot point here, then we have the torque from the crane, from the weight of the crane itself. Oh, we're already given a weight, so we don't need to do mg. We can just say weight times distance, which is halfway down, so that's 1.5, times sine of this angle. Let's see. If that angle, that's the same as this angle, which is the same as this angle, which would be 36.9. Okay. So that's sine of 36.9, and that's going to be counterclockwise. And then we have the weight of the stump and stuff all the way down at the end, times 3, times sine of the same thing. And then we have tension causing torque in the opposite direction. This is perpendicular, so we just have T times 3. That equals 0. We can solve for tension. We plug that in. That tension comes out to 1891 newtons. Then we can write forces in the x direction. We've got force from the hinge, x component minus a component of tension, which is going to be T cosine 36.9 equals 0. So we can, oops, there's the bell, solve for that. Sort is x, so that's going to be 1512. Oh, and it just asks for the horizontal and vertical directions, so we're not going to need to calculate a magnitude there. In the y direction, we have force from the hinge y component. We have a component of tension, and then we have the total weight, which is 800 plus 500. And so we can then calculate the y component of the force from the hinge. Which comes out to about 164 newtons. So that was a lot of problems to work through. Hopefully you get the idea. Yeah, I thought it was better to give more examples than less. And come to me if you have any questions.